Hello everyone, so this is the video for week 12, still about infinite series. We actually have learned like the 4 topics before, and now we go to the last subtopic, which is power series, Taylor and Maclaurin series. In this video we are going to learn about power series first, and I'm going to give you another video for the Taylor and Maclaurin series. So let's start. So power series, it's called power series because it deals with power inside as the sequence to be the series. So as you can see here, you can see a power up there. So power series is actually any series that can be written in the form of this. So the form is sum from n from 0 to infinity, and we have an times x minus c to the power of n. Okay, so this series is called a power series centered at c. So I'm going to discuss about what does it mean by center later, but just for you to know that this is the center of the series, and this is the power, and here you have our coefficient of the term. So what's so different from this series and the series that we have learned before? You see here that we have x. So before we learn about power series, when our series only change, the term of the series change only based on the n, or we have here is the working index here, and from 0 1 2 3 4. But now we also have x, so x here is our variable. Because we have a variable, we also can see this power series as a function of x. Because we can see it as a function of x, we can also see it with as a function that has domain and range. And that's why when we talk about the convergence of this power series, we will talk about also in what value of x that this series will converge. So what's so different from this series is it has x as a variable. So for some value of x, series may converge. For some others, it may diverge. Okay, so this is what we will learn in power series. Now, how to determine whether power series converges or not? Actually, we don't say that a power series will converge or diverge, but we are going to analyze to what value of x that does this power series converge. So when we talk about convergence of power series, we actually talk about to what value of x the series converge and diverge. Yes, indeed, that a power series may converge in all real numbers of x, and it may also diverge in all real value of x, but some series converge in some value of x and diverge in some others. So that's why we will need to analyze it. So the idea of convergence of power series actually comes from the idea of convergence in geometric series. Remember that if we have a geometric series, it will be in this form. So we have the sum of n starting from 0 to infinity, a, r, n, and r is actually the common ratio, right? So don't get confused with it started with n equals 0. Actually, it's the same with if I start with 1 and a, r, and minus 1. So it's actually the same. You don't have to worry about it. I just want you to know that in this power series, usually we always start with n equals 0. Okay, so in geometric series, we know that it will be convergent, the series will be convergent if the ratio, the absolute sign of the ratio will be less than or equal to 1, or you can say it's from -1 to 1. Okay, when the ratio is from -1 to 1, then you will get convergent series, convergent geometric series. So let's uh, make it a bit different. What if I change the ratio into a variable of x? So let's say I change this r into x. So I change the ratio, which is common, which doesn't change, into a value of x, which is variable that always change, that may change. So we don't have a fixed value, but we have a change value, ax to the power of n. So if we expand this series, we actually still have a very similar series to geometric series. We have a plus ax squared plus da da da, and actually the sum of that series, it's still the same, a to the power of 1 minus x, because we have here x is the ratio. So we have this is time x, this is also again times x. Okay, so we have this sum. So to get this sum, we actually need the series to be convergent. Okay, so in this case, we can say the series will be convergent when same thing, when the absolute sign of x is less than or equal to 1. So in our power series, the general form of it is like this. Here you go. So it's the same. So if we want this series to be convergent, we want the series to be convergent, we want that it has like the ratio. Let me put a note that ratio to be less than or equal to 1. So if we have this power series, actually we can know what value of x that makes this series convergent by having the ratio test. So same with it, if the series, so the series will converge if the limit of the ratio between a n plus 1 over a n is less than 1, and diverge when it's greater than 1 or infinity, and it's inconclusive when we have it's equal 1. Okay, so now let's try to an example. So we are going to analyze this series, this power series. So this series, we are going to determine to what value of x that this series convergent, or we call it intervals. This is like interval of x when the series converge. Okay, so we're going to analyze this by having the ratio test. So we will have limit n to infinity of a n plus 1 is actually x n plus 1 over n plus 1 over a n, which is x n over n. So we have limit n of x n plus 1 over n plus 1 times n over xn. So we can do cancellation here. We cancel this from x, and we actually have, we will have limit into infinity of x times n over n plus 1. So as you can see here that the limit, we evaluate a limit when n goes to infinity, so we don't really actually care with what happened with x here, right? So when we evaluate the limit, we consider the n only. We only consider this. So if we evaluate the limit of this, we will get that the limit of n over n plus 1 when n approaches infinity is actually 1. So the result for this is, actually just absolute x. Okay, so let me put notes. Of n plus 1 is actually 1. Okay, so we already know that we want it to be convergent, so we want the ratio to be less than 1. So we want this to be less than 1. So we can say that the series will converge if, so the absolute value of x less than 1, which actually it's the interval will be, because it's absolute value, the interval will be -1 to 1. So this is our interval of convergence. Here you go. What is the radius of convergence? So this is when we come up with our center. This is what we call the center. So we have, let me make so our radius of interval of convergence is started from -1 to 1, right? So this is interval of convergence. Okay, interval of convergence, and we have, this is x. In interval of convergence, and the radius of convergence means it's the same with the logic behind a circle. So you can see like the middle point from -1 to 1 is actually 0. So 0 is actually the center of the series. So this is the center of the series. So the radius is actually here. This is our radius. I will not write it as r so that you don't get confused with the ratio. So the radius is actually 1. We actually have a symbol for radius in this series is r, capital R, so r1. So the radius is actually the distance between the center to uh, the end point of the interval. So this is the radius, this one. Okay, so let me rewrite it. So the radius of convergence is 1, and the interval is from -1 to 1. Okay. Okay, so now I'm going to show you why, like, to visualize this series, what does it mean by it's convergent from x minus 1 to 1. Oh, here you go. Okay, so this is actually our series. So we have, this is our series here. So I just changed the n to I, so x to the power of I over I. So if I, so let's say we only need one expansion. So when n equal 1, then your series is actually on the x. So this is the visualization of the x over here. It's only a line, y equal x. When you change to n equal 2, then you will have this series. So you will get half x squared plus x over here. Okay, you have this. Okay, we know it will be convergent from -1 to 1. So if we change our n, see that the series will always convergent. You see that the series will always be monotone and bounded. See, and the value is goes to a certain value. And if you see here when x is greater than 1, here you see the value of the series goes to infinity. It's the same with when it's less than -1. Okay, so your series is actually become not convergent or divergent when it's greater than 1 and less than -1. And we cannot really determine whether it's convergent or not on the boundary here on x equal 1 and x equal -1. So this is how we analyze the convergence of power series. Okay, so in the next video we're going to learn about Taylor and Maclaurin series. So this is the continuation of the power series and this is the last part of our unit 3 module. Okay, thank you.